Hello friends, welcome to MATLAB school. In this video, we are going to simulate the vehicle dynamics. In addition to that, we are going to simulate the regenerative braking as well as friction disc braking uh, in EV employed with BLDC motor. So what we are doing here is we are giving the input in terms of kilometer per hour, and that speed is compared with the actual speed. So to give the torque, we are simulating the vehicle dynamics in terms of body load. So this is the block which is used to simulate the body conditions of the vehicle. So body conditions in the sense we will be giving the weight of the vehicle as input, then rolling resistance, rolling and driveline resistance coefficient, uh, aerodynamic drag, gravitational constant, and if you want we can give the initial velocity of the vehicle. So these are the basic parameters that we need to give as input to the block. And for the running time, we will be giving the speed or the velocity of the vehicle as one of the inputs. So this is the velocity of the vehicle, and this input xd dot is the acceleration of the vehicle. And if you want to simulate the vehicle's performance when the vehicle is made to run in a grade, even you can give the grade angle. So the given input will be in terms of kilometer per hour. So it has to be converted to RPM for the motor to understand. The motor can only understand the speed in terms of RPM or radians per second. Okay, so this is the battery which is connected to the motor. Further, it will give supply to the motor during motoring condition, and the energy will be transferred back to the battery during the time of regenerative braking. Okay, so with this block we are calculating the power uh, both during motoring and regenerative braking. So to facilitate friction braking simulation, we are using a longitudinal wheel disc brake. So here we can give the inputs such as uh, the uh, the details regarding the brake. So you can give wheel dynamics as input, like damping coefficient, wheel inertia, wheel initial angular velocity, all those things we can give. And also we can select the type of brake. We have a disc type brake, drum type of brake. So whichever we want we can select. See here I have selected disc type brake. Uh, the input braking pressure should be given in terms of pascals. So the brake pedal position will be converted to pascals. Okay, so what we are doing here is whenever the SOC of the battery is greater than 95, we will initiate friction braking in addition with the regenerative braking. The reason is when the SOC is greater than 95, we cannot, I mean the battery cannot accept more power. I mean the battery cannot accept further energy from the motor side during regenerative braking. So for that reason, to have effective braking, we are using the combination of regenerative braking and friction braking. So these are the inputs that we need to give as input to the wheel. Torque input, TFR is the torque input, and NFR is the speed input. Okay. So this if z is the weight of the body which acts along the x-axis, I mean z-axis. Okay. So inside this we have BLDC motor. So the BLDC motor, as you know, will be sensing the position of the rotor so that the corresponding stator windings can be excited. So to measure the position of the rotor, we are using 3 Hall sensors. The output of the Hall sensors is given as input to the decoder block. So this decoder block will convert the Hall values to corresponding EMF values. Basically, what we are doing here is we are predicting the direction of the back EMF. It can be it can be at the positive side or it can be at the negative side. Okay, and the output of this block is given as input to the next stage, where the gates are generated, gate signals are generated based on the EMF position or EMF values. Okay, so as you see, the EMF values are converted to gates switches, I mean gate pulses. Q1, Q2, Q3, Q4, Q5 and Q6 corresponds to the 6 switches in the inverter. Okay, so basically what these blocks are doing is it is converting the 3 input from the Hall sensors to 6 outputs, which is understandable by the switches in the inverter. Okay, here you can see the switches, right? So we are getting gates from this end, and through the other end we will be getting the variable PWM. I'll tell you the reason for this. The variable PWM only determines the voltage that the particular motor is receiving. Okay, so when the width of the pulse is reduced, obviously the motor will receive a lower voltage. Okay, so this is based on the speed input. So here we have the reference speed. It is coming from the previous previous input. Okay, so this is the reference speed. This reference speed is converted in terms of RPM, and this is the actual speed of the motor. Okay, the actual speed of the motor will be in terms of radians per second initially, and that will be converted to RPM by using this formula 30 by pi. So with this conversion, we are converting the speed which is already available in terms of radians per second, and it is converted to RPM. Okay, so here we are getting the value in RPM, and the actual speed is also in RPM. The error is computed, and the error is given as input to the PA controller. Okay, so this PA controller will vary the signal in between 0 and 1. The reason is this PWM generator block can understand only the values in between 0 and 1. If the value of or if the output of PI controller goes above 1, it will get saturated, because for any value above 1 it will read as 1. So for that reason we will be manipulating the error in between 0 and 1. So the output of PWM generator block will be pulses, as you know. So based on the input that it gets from the PI controller, the output width will get varied. Okay, so the output of this PWM will get varied based on the input that it gets from the PI controller. So during the time of motoring, the input will be coming from these 2 blocks or these 2 lines. Okay, and during the time of regenerative braking, the pulses will be going through this way. Okay, here what we are doing is I am just using the internal inductance of the BLDC motor to act as the boost converter. So here we are avoiding the usage of external boost converter and other complex circuitry. Okay, we are using the inverter switches as well as the internal inductance of the motor to perform the function of regenerative braking, right? So here the maximum current corresponds to the maximum rated current given in the nameplate details of the motor. So during the time of regenerative braking, the current flow will be in the reverse direction. Okay, so to mention that I am using a minus sign here. then the error will be calculated. Then it is given as input to the P controller. So based on the braking or position of brake pedal, uh, again this PWM generator will produce corresponding pulses. Okay, so as you see, I am switching off the upper half switches. This is the first switch, this is the third switch, and this is the fifth switch. First, second, third, fourth, fifth, sixth. So I am switching off the upper half switches during regenerative braking, and I will be giving variable pulses to the lower half switches. Okay, that is to the switches 2, 4 and 6 I am giving variable pulses. Okay, so that's all. And here we are calculating the efficiency of the motor. Efficiency of the motor during the time of regenerative braking. So let us run the model now. So before running the model, we have to specify the SOC value in workspace of MATLAB. I am giving the value as 50. Okay. Now I am going to run the model. Yes, the model is getting compiled. It's compiling. Yes, the model has started to run. Let us open the speed. Yes, we have given a speed of 40. So there's an initial overshoot and it will settle at 40 kilometer per hour. Okay, so this is the rated speed or the reference speed. So it is settling at 40 kilometer per hour. So let us now apply braking. So when we apply brake, this is electrical output. First of all, let us see the speed. So you can see the speed decreasing. So you can see the corresponding mechanical energy. So this is the mechanical energy produced during regenerative braking. This is the electrical energy produced during regenerative braking, and this is the efficiency during regenerative braking. So you can see the efficiency varies from point to point. Okay. And this is the regenerative brake force produced. So it is in terms of Newton meter. Okay. So this is the efficiency, motor, electrical output, mechanical output, and finally the speed. So mechanical in, and then electrical output. Okay. And this one is the regenerative braking force produced by the vehicle. Right. So this model is available for a download from the link given in the description. If you want, you can use it for your purposes. Okay, please subscribe our channel. Thanks for watching. Thank you.